6 aerodynamic modeling for complex configurations. The first example is a Airbus 380. Because the symmetry of the XZ plane, only half-span model is required. ZONAIR can compute the flow solution at asymmetric flight condition, including side slip angle, asymmetric control surface deflection, and so on, only using a half-span model. Internally, ZONAIR computes the symmetric and anti-symmetric ASC and superimpose the symmetric and anti-symmetric flow solutions to obtain the asymmetric flow solution. So this half-span model for Airbus 380. It consists of over 3,400 grids, over 3,000 sequence 4, and 181 sequence 3. And Winglet is modeled by the thin wing using the CL7 card. And on the pylons, the actual geometry of the pylon is that the pylon surface converges to a line at the end of the panel. However, the real flow condition, the flow does not stagnate at this line, but rather separate before this line. So to simulate such a flow separation before the end of the pylon, the after portion near the end of the pylon is truncated. So we introduce a hole at the end of the pylon. Then we put a set of a C-bar around this hole, and you can use the AUTOTIP cards. The wing trailing edge has two sets of a C-bar to simulate the wake behind the wing, one attached to the upper surface and one attached to the lower surface. This C-bar element for flat wake surface, it creates a flat wake surface by sweeping each C-bar to infinity. And on the upper surface between the pylon and the wing junction, the grid point 54787 is at the upper surface. The grid point 60010 is at the lower surface of the wing, and those two grid points also shared by the pylon. Okay, so you have to specify the RBE2, and then in the RBE2 you can say that the upper grid is 5478776. The lower grid is 60010. Then you say yes. So you can the RB2 will set up C-bars along those two lines, and then the grid point on the pylon behind this wing pylon junction is start from 54798 and 747989 and 60064. So the RB2 will separate those grid points into an upper surface and lower surface, and set up a two set of a C-bar along those grids. And likewise, you have to do the same thing along this side of the pylon, and to do the same thing along this side, using the RBE2. And for the Wing-Fuselage junction, you use you specify the RBE2, and which is starting from the upper surface at wing trailing edge, and the wing upper surface and the lower surface of the wing trailing edge between the wing body junction. And this RB2 then you specify a set of grid behind this wing body junction. So the RB2 will separate those grid points into upper grid and lower grid, and also set up two set of C-bar along those grid points. So you create, you will sweep, ZONAIR will sweep those C-bar down to infinity to create a two set of flat sheet of wing surface. For the engine nacelle modeling, and first of all, for you have an engine something like this, and you can use AUTOTIP to set up a C-bar around those lines, and the C-bar will create the wake to create a closure panel model. And in this region, and the flow can get out from the engine, so you have to use different P-shell for this region. And in the P-shell car, you specify the flow out condition, so the entry flow in equal to 100. And on the inlet face, you have to cover the inlet face by panels. And because in ZONAIR, you cannot play, any panel cannot have a 90-degree inclination angle. So you create a cone-like a model to cover up the inlet face. And those cone angle can be, say, 88 degrees. And you use those panels refer to P-shell car. And in the P-shell car, you specify the inflow condition to be 100%. If you don't do that, when the flow hits this panel, you will have it pass through a sharp turn here. So you're going to create a very low pressure region around this panel. But once you allow the flow to penetrate into those panel, this low pressure region problem will disappear. And then for the vertical tail and the horizontal tail, and because if you create this model from the CAD model, and it's very difficult to separate the trailing edge and the tip into upper grid and lower grid. So you have to use slice. For the horizontal tail, you specify a slice. So you starting from this point, and then you go to this point, and then the initial surge vector is this grid. Okay, and so the slice car will slice the trailing edge of the tail into an upper surface and lower surface, and meanwhile it will place the C-bars along those two set of grids. And then you say yes, so you will create a RB2 here. And meanwhile, you want to slice the tip into an upper and lower side grid. Meanwhile, you want to create two set of a C-rod. And so the slice car will slice from here to there to this grid, and the initial surge vector is defined by this grid. So you create an initial surge vector, and so the slice car can slice this wingtip into upper grid and lower grid. Meanwhile, you will put two set of a C-rod along here, and since it's a half-span model, so the vertical tail only has a right-hand side model. So you want to use the auto rod to place the C-rod along here, and you want to use auto bar to create a C-bar around the trailing edge of the tail. Then you create a specified RB2 here, and then you will create C-bars around this line. Then you use auto bar to create C-bars around the end of the fuselage. And because the winglet is very thin configuration, so we want to use thin wing modeling, and so we use 3 set of CO7 with those ID. Because of the winglet, the vortex roll up along the wing tip should not be modeled. So only one side of grid along the close edge of the wing tip is modeled. Therefore, you don't need to put C-rod in. And you should group the aerodynamic component into different P-shell car and matte body car. And this later on you will find out is very useful to set up a spline input card, and also you can define component loads using the load marker, and it's easier to define a control surface, or you can introduce the flow in boundary condition. So we want to group the AUTOTIP panel by this P-shell car, the rudder by another set of P-shell car, and this horizontal, this elevator, this pylon, this wing, and this engine outlet, and this engine and the engine inlet face panel. So you group them in by different P-shell car. And this is the F-15 configuration. Again, we use a half-span model, and it consists of about 3,100 grid and close to 3,000 C-4 and close to 170 C-3. And first, we want to slice the wing trailing edge using the slice car, and because this trailing edge is not a straight line, so you have to using 2 slice car, and the first slice car here, and then at this point you don't want to separate the grid into upper and lower surface. Then you use another slice car, and then this slice car will separate this grid to upper and lower surface, and meanwhile we separate those grid into upper and lower surface. Then you create a RBE2 along this side, and also for the trailing edge of the tail, you also use the slice car. You also use the slice car for the vertical tail trailing edge. But however, when you use the slice car to slice the vertical wing trailing edge, and right here you start you generate the RBE2, and so when the slice car try to separate this line to a right hand side grid and lower side grid, and the slice car when you slice here, and then we find out all the panels along shared by this grid that all belong to the right hand side. So then the slice car will generate a fatal error. Okay, to circumvent this problem, and for the P-shell car of those panels in the P-shell car, you have to use the so-called the offset. Okay. And so you offset the Y position of those panels control point to a large positive value. So the slice car will use this offset grid point to determine which panel belong to the right hand side, which panel belong to the left hand side. And then we truncate out the engine nacelle. And then we place the C-bar around this line, and then the C-bar will create a weak surface to satisfy the closure condition. And also the inlet face panel we refer to a P-shell car. In the P-shell car, we specify 100% of the flow-in condition. And this is a conceptual aircraft, and we model this aircraft using over 1,400 grids and about 12,000 C-4 and close to 100 C-3. And this because the wing wake generated by the C-bar along the trailing edge of the wing can penetrate into the fuselage, and so there's a flat wake surface from the wing trailing edge penetrate into the after fuselage and create a numerical singularity. This issue can be resolved by using the Winglet, okay, that model a curved wake. So we first, when we slice this wing trailing edge, we put a negative sign. So no C-bar is generated from the trailing edge of the wing, and then in this entry we say no C-bar. So the RBE2 will not place C-bar along this line. Then instead we attach a curved wake surface to the trailing edge of the wing, and also connect to this RBE2 line, and using the Winglet. Okay, so in so doing, we create a curved wake, so the wake cannot penetrate into the body. And the next sample case is a DLR F-6 configuration. The objectives of this test case are to present the best panel modeling approach of the wingtip, to show the impact of panel density near the wing trailing edge on aerodynamic solution. And this configuration is a fuselage wing pylon engine transport aircraft. The unstructured safety surface match can be downloaded from this website. And the pressure coefficient contour at Mach number 0.6 and angle at 3 degrees is computed by Fun3D Nacelle solver to serve as a reference solution to investigate the best panel modeling approach for this configuration. So based on the safety surface match, a half-span ZONAIR model is created, and that consists of 9,000 grids and over 8,800 panels. The wingtip panel of this model is automatically generated using the AUTOTIP card. AUTOTIP cards create two sets of a C-rod along the upper and lower side of panel. Also create and create two sets of grid, one attached to the upper panel, another one attached to the lower panel, and C-rod, two sets of C-rod are generated along this line, and then the C-bar here, we use the PA-PB entry to generate an infinite line vortex. And then we use this model, we compare the ZONAIR CP solution with the Fun3D solution. You can see we have a pretty large discrepancy. And then where the problem come from? And if you look at the CP at the wingtip, you have a very large negative pressure region. Okay, and so the problem is that angle between those panels on the wingtip generated by the AUTOTIP card and the panel on the wing upper and the lower surface has a 90-degree angle. So when the flow roll up from the lower wing surface to the wingtip, it will pass through a 90-degree turn. This 90-degree turn will generate a very high velocity, thereby very low pressure region, because the ZONAIR is based on attached flow assumption. So this high flow velocity contaminates the entire flow solution on the wing, and so this panel modeling is a poor panel modeling. So instead of the 90 degree, we create a wrong wing tip model. Okay, so we avoid this 90-degree turn. Then this time, if you compare the wingtip CP computed by ZONAIR and the CFD, we have a very similar result. And then we compare the CR with angle attack, CM with angle attack. The lift coefficient at all angle attack computed by ZONAIR are significantly and consistently higher than those computed by from 3D, and the pitch moment CM are lower. Okay, so pitch moment is lower and CR is higher. Then if we look at the CP Chordwise distribution along those span station, you can see first ZONAIR under predict the spike along the wing tip, wing leading edge, and this is expected because the CFD mesh is much denser than ZONAIR along the leading edge, and because ZONAIR CP the spike along the leading edge is lower than the CFD. So when you integrate the CP, the CL should be lower than the from 3D computed CL. However, ZONAIR generate a higher CL. So apparently, this problem is because the wing trailing edge CP. If you look at the wing trailing edge CP, the net CP is lower surface minus upper surface. Because then you can see that the net lift generated by ZONAIR along the wing trailing edge is higher than the from 3D solution. Therefore, it give you higher CL. And meanwhile, because this portion of the higher lift will create a nose down pitch angle, and therefore the CM is under predict when compared to the from 3D. So apparently, the density of the panel along the wing trailing edge is not high enough. So we create a refined wing trailing edge panel model. You can see we have increase the density along the wing trailing edge, and this is the coarse panel model. So when we refined the wing trailing edge panel, this time we had a much better agreement with the from 3D. And then if you look at the panel, the CP along the Chordwise at the trailing edge, and this time we have much better agreement with the from 3D solution. So this is the reason we can have a much better agreement of CR and CM between the ZONAIR solution and the from 3D solution. Okay, this is the end of chapter 6.